Welcome to Calculus. Today we are going to explore a beautiful and fundamental principle known as the intermediate value theorem. This theorem might seem like simple common sense at first, but it is actually a massive pillar of modern mathematics and computer science. It gives us a strict mathematical guarantee about how continuous processes behave, ensuring that things do not just magically teleport from one state to another. Let us dive in and see how this works. To understand what this theorem is all about, imagine you are driving a car on a straight highway. When you start your journey, your speedometer reads 0 miles per hour. A few minutes later, you look down and see that you are traveling at 60 miles per hour. Common sense tells you that at some exact moment during those few minutes, your car must have been traveling at exactly 30 miles per hour. Your speed cannot magically jump from 0 to 60 without passing through every single number in between. There are no teleportation tricks in smooth, continuous processes. Now that we have the everyday intuition, let us translate this common sense idea into a strict mathematical rule. In calculus, we apply this to what we call a continuous function on a closed interval. A continuous function simply means a curve that you can draw from start to finish without ever lifting your pencil off the paper. The closed interval is just a specific range of numbers on the horizontal axis, starting at A and ending at B. So your function starts at a specific height and ends at another height. The theorem tells us what happens in between. This brings us to the formal statement of the theorem. If you pick any target height, which we call k, that lies strictly between your starting height and your ending height, the theorem guarantees a specific result. It states that there is at least one specific input value, let us call it c, where the function hits that exact target height k. In our formula, f is the continuous function representing our changing quantity. The symbol C represents the specific input value, like a specific time on a clock, that exists somewhere between our starting and ending points. And K represents the target output value, like a specific speed. If the target changes, the theorem promises we can always find a corresponding input to make this equation true. Before we move on to the proof, let us see this with a concrete example. We will look at a classic mathematical problem, proving that a specific equation has a solution, even if we cannot easily find what that solution is. We are asked to prove that a polynomial equation has at least one valid solution or root strictly between 0 and 1. Our strategy is to treat the left side of the equation as a continuous function. Because it is a polynomial, it has no breaks or jumps. We begin by plugging our starting boundary value, 0, directly into the function. The calculation simplifies down to positive 1, meaning the graph starts above the horizontal axis. Continuing with our example, we now test the other end of our interval. We plug our ending boundary value, 1, into the exact same function. The math simplifies to -2. This tells us that at the end of our chosen interval, the graph has dropped down below the horizontal axis. We can now clearly see the complete picture. Our target value is 0, which represents the axis itself. Because 0 lies strictly between our ending height of -2 and our starting height of +1, the unbroken curve must cross the 0 mark. Therefore, the theorem guarantees a specific number exists where the function equals exactly 0, proving our solution exists. Let us look at a second example, this time involving trigonometry, where standard algebra cannot isolate the variable. We want to prove there is a specific angle where its cosine is exactly equal to the angle itself. To use our theorem, we first rearrange the equation by moving everything to one side, leaving a 0 on the other. This creates a brand new continuous function, which we will call g of x. We will test this function over a logical interval from 0 to pi/2. Plugging in 0, the cosine of 0 is 1, leaving us with a starting height of +1. Now we test the ending point of a chosen interval. We plug in pi/2. The cosine of pi/2 is exactly 0. Subtracting pi over 2 leaves us with a negative result. So, by the time our function reaches the end of the interval, it has plunged down to a negative height. Our ultimate goal was to find a point where the function equals 0. We have successfully shown that the function starts positive and ends negative. Because the curve is unbroken, it absolutely must cross the horizontal axis. At that exact crossing point, the function equals 0, which proves beyond a doubt that such an angle truly exists. Now that we have used this formula in multiple examples, let us understand where it comes from and prove it is an absolute mathematical certainty. We will assume our starting height is strictly less than our target and our ending height is strictly greater. To build our proof, we rely on a fundamental rule of numbers called the completeness axiom. This axiom states that any collection of numbers that has a ceiling must have a strict exact least upper bound. We start by creating a specific collection or set called S. This set contains all the input values between our start and end where the function's height is strictly less than our target. Because the starting point is below the target, this set is not empty and it is trapped inside our interval. Continuing with our proof, because our set has an upper limit, the completeness axiom guarantees it has a supremum, which is the absolute smallest upper boundary. We will call this special boundary number C. Our goal now is to prove that the function's value at this exact boundary point is exactly equal to our target. We do this by logically ruling out the only other two possibilities. First, let us imagine a fake scenario where the height at our boundary is strictly less than the target. Because the function is continuous and cannot teleport, it would have to stay below the target for a tiny distance slightly to the right of C as well. But that means those points should also be inside our set, which completely contradicts our definition of C as the absolute upper boundary. So this scenario is impossible. This brings us to the final step of our proof. Let us imagine the opposite fake scenario. What if the height at our boundary is strictly greater than the target? Again, because the function is continuous, it would have to be greater than the target for a tiny distance slightly to the left of C as well. If that were true, then no points immediately to the left of C could possibly belong to our set. This would mean we could find a much smaller upper boundary for our set than C, which contradicts the fact that C is the absolute smallest upper bound. We have logically eliminated the possibility that the height is less than the target and that it is greater than the target. By the basic rules of numbers, the only remaining possibility is that the height at C is exactly equal to our target. The theorem is proven. Now that we have proven it mathematically, let us look at exactly what this means visually. On the screen, you see a graph with a smooth blue curve representing our continuous function. Notice how it starts at a specific point on the left below the red dashed line and ends at a point on the right above the red dashed line. The red dashed line represents our target height, K. Because the blue curve is unbroken, it is physically impossible to draw it from start to finish without crossing that red line. The exact point where they intersect drops down to the horizontal axis at the value C. This diagram perfectly captures the physical reality of the mathematical proof we just completed. So, we have proven that this theorem holds, and we have seen it visually. This brings us to why it actually matters in the real world. The intermediate value theorem might seem like simple common sense, but it is a massive pillar of modern mathematics and computer science. When an engineer needs to find the exact temperature where a chemical reaction stabilizes, the equations are often too complex to solve by hand. Instead, computers use algorithms based on this theorem, like the bisection method, to trap the answer between a positive and negative value, slowly narrowing the gap. Without this theorem, we would have no mathematical guarantee that these computer algorithms would ever actually find the correct answer. To wrap up our lecture, let us review the key takeaways. The intermediate value theorem is, at its core, a formal mathematical guarantee of continuity. It promises that a continuous function moving from point A to point B must pass through every single value in between. Whether you are tracking the speed of a car, the temperature of a room, or complex mathematical curves, you cannot skip steps. If you start above a line and end below it, you absolutely must cross that line somewhere along the way. You now have a solid understanding of both the intuition and the rigorous proof behind this fundamental concept. Great job following along.